All right, let's dive into one of the biggest ideas in all of science, Albert Einstein's theory of relativity. And look, this isn't just some dry physics lesson. This is a story. It's the story of how our entire understanding of reality, of space, of time, of gravity itself was completely flipped on its head by one person's incredible imagination. It all started with a single, absolutely radical question. For centuries, everybody just accepted what Isaac Newton told us. Gravity is an invisible force, like a rope, pulling things together. But Einstein dared to ask something that sounded, well, kind of crazy. He said, hold on, what if gravity isn't a force at all? What if it's something way weirder, something woven into the very fabric of the universe? And this chart right here, this is the whole revolution in a nutshell. On one side, you have the old school Newtonian world. It's predictable, right? Space is just a big empty box, and time is this universal clock that ticks the same for everyone everywhere. But then, on the other side, you have Einstein's universe, and it's alive. Space and time are tangled together. They can stretch and bend. And gravity? Well, gravity is just what you feel when you're moving through those curves. It's a total paradigm shift. To really get how huge Einstein's idea was, we have to first understand the world he was born into. A universe that, for all intents and purposes, seemed to run like a perfect, predictable machine. Think about it. It just makes sense. You've got 3 dimensions: length, width, and height. That's your stage. And time. Well, time was the director. It was absolute. A second on Earth was a second on Mars, was a second in some distant galaxy. It was this master clock for the whole cosmos, and it didn't care what you were doing. For hundreds of years, this common sense view worked like a charm. Until, suddenly, it didn't. So, the first crack in this perfect clockwork universe came from a really strange place: light. It turns out light is a total rule breaker, and it created a major crisis for physicists. Okay, this is where your brain might start to feel a little fuzzy, but stick with me. If a baseball is flying at you and you run towards it, it seems to be going faster, right? That's just common sense. But light doesn't care about common sense. Scientists discovered that whether you're rocketing towards a light beam or running away from it as fast as you can, you'll always measure its speed as the exact same number. This one single stubborn fact just completely shattered classical physics. And this leads us to a fantastic real-world mystery. Up in our atmosphere, these little particles called muons are being created all the time. But here's the thing. They have a ridiculously short lifespan, just 2.2 microseconds. I mean, that's nothing. Even if they travel at almost the speed of light, there is no way they should have enough time to reach the ground before they just, poof, decay. And yet, here we are, detecting them on the Earth's surface all the time. How? How is that possible? It's a paradox that just shouldn't exist. Well, in 1905, a young Albert Einstein comes along and solves the whole puzzle. He proposed that in order for the speed of light to be constant for everyone, something else has to be flexible. And that something else was our understanding of space and time. This was his theory of special relativity. Einstein realized that space and time are not separate things. They're actually woven together into one unified 4-dimensional fabric called spacetime. A mathematician named Hermann Minkowski put it beautifully. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows. It wasn't just a cool concept. It was the new stage for reality itself. So, how does this new reality solve our muon mystery? Simple. Because those muons are traveling so incredibly fast, their internal clock actually ticks slower than ours. We call this time dilation. From the muon's point of view, its life is still a fleeting 2.2 microseconds. But for us, watching it from Earth, its clock is in slow motion, giving it way more than enough time to reach us before it decays. The paradox vanishes. The faster you move through space, the slower you move through time. And as if rewriting space and time wasn't enough for 1 year, special relativity also gave us the most famous equation in all of physics, E equals mc squared. It's a surprisingly simple formula that holds a profound secret. Mass and energy are basically the same thing. They're 2 sides of the same coin. It tells us that you can convert a tiny, tiny amount of matter into a spectacular amount of energy. Now, special relativity was a masterpiece, but it was incomplete. It only worked for things moving at a constant speed. It didn't account for acceleration, and it left out the biggest force in the cosmos, gravity. So Einstein went back to the drawing board for another 10 years. And then he had what he called his happiest thought. He imagined a person in an elevator in deep space with no windows.
If that elevator started accelerating upwards, the person would feel their feet pressed to the floor. Now, how is that any different from the feeling of standing still on Earth? The answer is, it isn't. You couldn't tell the difference. He realized that gravity and acceleration are indistinguishable. They're equivalent. And that was the key.
This thought led him to his incredible conclusion. If gravity feels exactly like acceleration, and we already know that motion affects spacetime, then gravity must not be a force at all. Gravity is geometry. Heavy things like stars and planets don't pull on other things. What they actually do is bend and warp the fabric of spacetime around them. The physicist John Archibald Wheeler came up with this brilliant, elegant sentence that sums up the entire theory of general relativity perfectly. It's this beautiful dance. The amount of stuff, matter, and energy tells spacetime how it should bend, and then that curved spacetime tells the stuff how it should move. You know the classic analogy, right? Imagine a big, stretchy rubber sheet. That's spacetime. Now you place a heavy bowling ball, that's our sun, in the middle. It creates this deep dip, a curve in the sheet. If you then roll a little marble, that's the Earth, nearby, it doesn't get pulled towards the bowling ball. It just follows the curve. It's traveling in the straightest possible line through a curved space. And that path is what we call an orbit. That's gravity.
So at this point, you might be thinking, okay, this is some seriously cool cosmic level stuff, but does it really matter to me? And the answer is a huge, emphatic yes. Relativity isn't just an abstract theory. It has very real consequences that impact our technology and our view of the universe.
Take the GPS on your phone. The clocks on those satellites in orbit are moving really fast, and they're in a weaker gravitational field, so their time literally ticks a tiny bit faster than ours. If engineers didn't constantly correct for these relativistic effects, your GPS would be off by several miles every single day. We've also seen light from distant stars literally bending as it passes the sun, just as Einstein predicted. The theory gives us black holes, it predicted gravitational waves, ripples in spacetime that we finally detected in 2015. Our entire understanding of the Big Bang rests on this theory.
So in the end, what Einstein did was give us a whole new cosmos. He took us from Newton's rigid clockwork universe and dropped us into this dynamic, flexible, and honestly much more amazing place, where space and time are active players in this grand cosmic dance.
And that leaves us with the biggest puzzle in physics today. General relativity is the king when it comes to the big stuff, stars, galaxies, the universe. But for the world of the very, very small, we have a different set of rules called quantum mechanics. And here's the problem. The two theories are both spectacularly successful, but they absolutely refuse to play nicely together. They don't work in the same sandbox. So the quest to unite them, to find a single theory of everything, is what drives physics forward, leaving all of us to wonder, what's the next great revolution just waiting to be discovered?